All right, welcome back, Gen Chem 1 students. Today we're going to start probably the most important chapter in the entire book. Right now, the chapter we're learning, I guarantee you, is the key to every chemical reaction there is. You know what? Right now, the stuff we're going to talk about today, they're trying to use to figure out how to beat this virus, how to create the vaccine, how to find a drug that can somehow be used to help fight it while in the hospital. This is the most important chapter in the whole book. This is on, we're going to start chapter 9. On molecular geometry. Alright, so in chapter 8, focused a lot on Lewis structures and that whole practice sheet. Hopefully you went along, you got that down, you're ready to build those. You got the concept of resonance down. Yeah, that's the foundation. Because without that, you cannot determine molecular shape. You have to first know how the atoms are bonded together. Are there single bonds? Are there double bonds? Are there lone pairs? All of that is critical. That is step number 1. You have to master that. If not, give me a call. Hit me up. We'll set up tutoring session. I will do whatever I can to help you understand Lewis structures, because without Lewis structures, this chapter you won't be able to get the correct answers on the molecular geometry. Now, why is geometry so important? Remember, there is no such thing as atomic intelligence. There is no such thing as molecular intelligence. Molecules don't know what they're supposed to do. A medicine, you say you got an ache in your arm. It doesn't know. When you swallow ibuprofen or Motrin or any of those, it doesn't know your arm hurts. It doesn't know that's what it's supposed to do. It's just that there's a molecule has a shape, and the shape will either be attracted to a receptor or it will not. There's just, does it fit together like puzzle pieces? And are the two molecules or portions of the molecules, are they attracted to one another? So right now we're trying to find something that will be attracted to that virus, that COVID-19, that will bond to that virus and then be able to deactivate it, to destroy it, to bond. But again, it's not going to know. That's the purpose. All it's going to know is that it fits and it's attracted. And then that attraction is going to deactivate, prevent the mechanisms that would have normally proceeded. So this is a big one. And what we're going to be doing, I'm going to be combining a bunch of different sections together. I teach it all at once. They essentially just keep repeating, and I think it's much easier if I just show you how this all works. We're going to step through it one at a time. I'm going to give you a website that I think is going to be very useful, and we'll go through how you determine molecular shapes. Now, the model we're going to be using is called the Vesper model, and that's, while it's pronounced Vesper, it's spelled V-S-E-P-R. And that stands for valence, shell, electron, pair, repulsion theory. Right, so the Vesper theory. Valence shell electrons. All right, valence shell, that means outer shell. So the outer shell electrons, right, they're either pairs, that means non-bonding, or bonding. Both are counted. They repel each other. And that dictates the shape. When we have bonded atoms, they're repelled from another set of bonded electrons to another atom, but they're also repelled by lone pairs of electrons. So that's what we needed chapter 8 for. Figure out how many bonds there are. Are they single bonds? Are they double bonds? Are they triple bonds? And how many lone pairs of electrons there are. Alright, so now, one of the things you're going to see in the book is this AB nomenclature stuff. Ignore it. Completely unnecessary layer of jargon. That's completely unnecessary to actually learn this chapter. Frustrates me that all the books put this, well, not all the books, some of the books put it in. Some call it the AB, some call it the AXE method. We don't need it. Alright, so what do we need? What we need for this chapter is to set up a table. Now, our table is going to start with the number of electron regions. That's going to be the first column in our table. Now, we're going to have to define what I mean by an electron region in a second. We'll get there. We're going to need to know the number of lone pair electrons. All right. From that, we have enough information to determine the electron geometry. All right. Now, the electron geometry, that's going to tell us where in space we can find both the bonding and the non-bonding electrons. That may be the same, but sometimes it's different than what is the molecular geometry. Now, the molecular geometry is where are the atoms. That can be different than where are the electrons because non-bonding electrons. Right? Non-bonding, those pairs that just sit on the central atom, they're not bonded to another atom, but they do repel the single bonds. They repel the double bonds. So that's why the electron geometry can be different than the molecular geometry. Now, there's going to be one more column. We're not going to get to this probably in this lecture, but make it in your notes because we have one more one more column, and that's going to be the hybrid orbitals. All right, that column's probably going to be unfinished till a later lecture. All right. So, we're going to start with the simplest and work to the most complex. But the first thing I need to do is define this idea of electron regions. What do I mean by an electron region? Alright, well, an electron region, this is electrons that are confined to a single space that can't move apart. Alright, so what do I mean by that? A single bond equals one region. There's two electrons in that region, and that region acts as a single unit. Alright, a lone pair of electrons, that acts as a single unit. When we're looking at what repels each other, a lone pair will act as one region. Alright? So a single bond is one region, a lone pair of electrons is equal to one region. So far, most people are pretty good with that. Where it gets, some people don't like this. A double bond is equal to one region. Now it has two bonds, but those bonds, they can't move away from each other. They're stuck in the same region. So they act as a single repulsive unit in this valence shell electron pair repulsion theory. A double bond acts as a single repulsive unit of electrons. And the same goes for a triple bond. In the triple bond, they act as one region. Now, at the in one or two more lectures, we'll actually look exactly how a double bond forms, what orbitals are used. We'll look at exactly what a triple bond looks like. And then you go, oh, okay, that's why it was one region. So for now, you got to give me a little bit of trust on why this works. So essentially, any kind of bond is just simply one region. A lone pair is one region. All right. So when we look at the simplest molecule, we're going to have, let me give you an example. Something like maybe carbon dioxide. Whoops, I drew one too many pairs of electrons on that oxygen. Let me erase that. All right, there we go. Now, when we count the number of electron regions and lone pairs, we are always looking at the central atom, nothing else. So on carbon, how many regions are there? Well, there are two regions, right? Because a double bond is one region. So I find that there are two regions. All right. Now, when you have two regions on a center atom, well, let's look at a model of this. Let me pull up a website for you guys. All right. This website, let me see if it writes on the screen. It does not write on the screen. Let me go back. All right, this website, I'm going to put this up on top here. If you just Google PHET and then Vesper, whoops, you'll get this website. It's at the University of Colorado. And it is a very cool, very simple, user-friendly program. All right, so here we have in purple a center atom. And I've added two electron regions. Just to keep it simple, I added two lone pairs. So right here, you can see you can remove them and you can add them. And then you can rotate this molecule however you want to help visualize. So I encourage, you're going to see I'm going to keep popping back and forth to this website to build molecules. Now, the two electron regions want to be as far apart from each other as they can. That's the whole valence shell electron pair repulsion theory. So these two regions got as far apart away from each other as they can. So they're 180 degrees from one another. So I have, let me fill in my chart. I have two regions. None of them are lone pairs in carbon dioxide, right? Now, where are my electrons? Well, my electron geometry, it is called linear because they're 180 degrees, right, from each other. Anytime you have two regions and zero lone pairs, it's always linear. Now, let's build the molecule. We don't really have two. That was the electrons. I was just showing electrons. Now let's look at where the atoms really are. All right, so I have a double bond and another one. And it should be no surprise. Let's rotate that around. The electrons are at the end of each region, right? So I have a linear molecule. And right, whenever you have zero lone pairs, your electron and your molecular geometry will always be identical. Always, always, always. All right. So now, oh, I should have said here, another great way, especially when we start getting some more complex ones, some people love to look at those, the PhET program, those three-dimensional models just make sense to them visually. Other people are more tactile learners, and making models works better for them. If we had been at IVCC, I would have brought out a bunch of those kids' magnet toys. They're little spheres and little sticks with magnets in them that you can put on a sphere. I would have had you building them that way. When I was a freshman in Gen Chem, my professor said marshmallows, toothpicks, or gummy candies and toothpicks, but build them, see them, learn them. So some people, just that act of building them really helps. So if you're a visual learner, yeah, great. If you're more of a tactile, if it helps to see it that way, then by all means hit pause, go raid the cupboard, and find some marshmallows or candies and some toothpicks. Come on back. All right, now the next one. All right, whoops, let me change back to black. 3, 0. All right, we're going to put 3 regions around, and they're just going to be, or there's going to be no lone pairs. So if I pull up my program, I'm going to delete those bonds. For electron geometry, so that you're not looking at atoms, I always just use the lone pair. So pop in 3 of them. All right. Now, all right, I tip it on its side so that you can see this molecule is flat. All right, and then I'm going to rotate it this way so you can see the shape. Now, the names of these shapes, very often, the name is based on what would happen if you connected the outside points of all the electron regions. So I hope it will make sense to you that you can see the triangle, the 3 sides. If you can see the mouse on the screen, you see the triangle it's outlining. There's no bonds there, there's no electrons there, it's just what the shape would be as if you made it a solid. Now that right there is a triangle. So triangle is part of our name. But the rest of the name comes from the fact that the molecule is flat. So let me pop back over. 3,0 is called trigonal planar. And again, because I have 0, my molecular geometry is also trigonal planar. All right. So far, so good. Well, now we're gonna change it up. We're gonna throw in a set of lone pairs. So I'm gonna have 3, but one of those 3. Now this is the number of lone pairs. The lone pairs are counted in here. They're not separated, so we have 3 total. Actually, I'm gonna put total up there on top. We have 3 total. One of those 3 is a lone pair. Now, this always, the number of total regions always dictates electron geometry. If it's 3, it's trigonal planar, done. No ifs, ands, or buts. Anything with 3 regions is trigonal planar, automatic. But now, I've changed it. I've got 1 lone pair. All right. So let's jump over to our molecular model and build it. Let's see what it looks like. I'm going to get rid of those. Now, if I had 3 regions, single bond, I got 2 regions, but now I throw in my 3rd region, 3 total regions, 1's a lone pair. All right. Right there is my shape. Now you can see that the angle between the 2 atoms is 120 degrees. But so is the angle, or very close to 120 degrees, between the lone pair and the single bond. It changes just a bit, but for Gen Chem 1, we're going to call it 120. All right. So let's go back to our table. Actually, let's talk about the name first. What is the name of the electron geometry? Is still trigonal planar. The molecular geometry, see, we're only concerned where the atoms are. This is called the bent geometry. All right, so now the trigonal planar, I forgot to put in that, it's 120 degrees, right? So hopefully that you can see that makes sense. We still have our trigonal planar electron geometry, but our molecule is bent. All right. Now, so far so good, hopefully. We're going to continue our table on. And the visualization is about to take a jump. This one's a little harder to visualize. We're going to start with 4 regions, 0 lone pairs. All right, what does 4 regions around the central atom look like? All right, 1, 2, 3, and we're going to add a 4th in. All right, now let's spin this around a little bit. All right. Trying to get the right angle. Okay. So, if you look at this shape right now, in the purple center atom is in the center. There are 3 electron regions around the base. They're kind of pointing downwards, and one is pointed upward. All right, this shape, and I'm going to draw this another way back on our sheet. You have the center atom. I'm just going to fill that one in. And then you got one that goes up, and then 3 pointed downwards from the base. That is the shape. Just using lines now. Alright, this is one that really helps to build. So if you were going, I don't need this, maybe now you're going, what? Go build it. Get your marshmallows, get your candies. Visualize it by building it. Now, this shape is called the tetrahedral. Tetra stands for 4. There, if you were to connect, let me draw this base in. Right? That's considered a side, those dashed lines. So it's resting on its bottom. If you tip it over, it would be resting on a new base. There's 4 bases to it. Google it, do tetrahedral geometry, hit Google, hit enter. Oh hell, why don't I do that? See if we can find something that will help you visualize it. Alright, let's go to images. Now some of these are going to be showing electron geometries, and that's fine. Alright, so you can see the tetrahedral shape. We've got a number of them. If any of you know what a 4-sided dice looks like, right? Now, half the class went, what's a 4-sided dice? Do they really make such a thing? Yes, they do. And to the other half who go, oh, I know what a 4-sided dice is. I know you've wasted a lot of time. Lots of time of your youth has been already wasted. Yeah, I'm a D&D nerd too. So, anyway, or was once upon a time. It's a gaming dice. A D4 in the lingo of fellow nerds. So, the tetrahedral shape. All right. This is key for those who go on to organic chemistry. It is the favorite shape, or one of the main shapes carbon takes in compounds. All right. Now, let's go back here. All right. So we've got our tetrahedral shape. Because it is 0, the molecular shape is also tetrahedral. All right. Now, go in here. Let me put in 4 bonds quick. You know what? I think it might be easier to visualize using bonds. Alright, play with this program, visualize them, rotate them, count the 4 sides, right? There's 1. I bring that down, now it's sitting on 2. And I think that's 3, and I've lost visually where the 4th one was, but you get the point. Now, what happens when I replace one of my bonds with a lone pair of electrons? This is our next one. This is our 3-1. Let's pop back over to our chart, fill in our chart quick. Oops. This is going to be 4 total regions. One of them is a lone pair. 4 regions tells me it has to be a tetrahedral. But because I've got a lone pair, my molecule has changed shapes, of course. Alright, so now I'm only concerned where my atoms are. And the name of the shape, let me try and get these under control a little bit. Here we go. When you're looking at this shape, purple atom is at the peak of, let me put it this way, looking down on it, that's a pyramid. Right, let me take it from a side shot. Can you see the pyramid? But the pyramid, there's 2 types of pyramids, and they're defined by their base. You can see the base, doing a shot from underneath, there are 3 atoms making up the base. So this shape is called the trigonal pyramidal. All right. Now, we can do another one. We can do a 4, 2. We can have 4 total regions where there's 2 lone pairs. All right, well, 4 tells us it's still tetrahedral. But now, 2 lone pairs. Let's jump over to our model. Let's get rid of one of our bonds and add in 2 lone pairs. All right. So you can still see there's a tetrahedral shape of electrons. What I want to know is what's the shape? Not looking at the electron clouds, but just the atoms. You've already seen that shape. That shape is bent, because there's more than one way to get bent. This is when I would have paused, looked out at the group for all the chuckles, for everyone laughing about multiple ways to get bent. Ha 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 ha. Funny joke. Yeah, works every year. Alright, and that's also how I identify the jokers in the class. Too bad I can't do that online. Alright, now, what am I doing here? Trying to extend my graph. Now we're going to go up one more. 5 regions, 0 lone pairs. I'm going to jump over to my model. And you know what? I'm just going to put in 5 single bonds. I think the single bonds actually work better for visualizing the geometry. We're going to try this here. Let me get this arranged right. Okay. Now, let's jump to my table first. Tetrahedral is 109.5 degrees between bonds. I should have put that in. Now, back to trying to visualize this one. There's a difference in positions. The right way to look at this, and when you build it, whether it's out of marshmallows or here online, there are 3 bonds, or the 3 that go around the center, and then there's a North Pole and a South Pole, kind of. And actually, around the center, those are called equatorial positions. And then we also have, get this, Sorry about that. All right, we've got our equatorial positions, and then we have our axial positions. So you should make a note of that. The equatorial positions around the center, axial are the north and south. And you notice I have two different bond angles. I'm going to change this to look down from the top. You can see about 120 degrees around the equatorial position. All right, now I'm going to turn this back up. Now, if you look at the angle between an axial and the equatorial atoms, it's a 90-degree angle. So there are differences. There is the two polar positions and three axial positions, or sorry, three equatorial positions, two axial or polar positions. All right. Now, this geometry, if we're just looking at electrons, not where the atoms are, but if we look at just the electrons, this is called trigonal. Actually, let me go back and show you the name. Okay, the triangle comes from the shape of the equatorial. You can see the triangle. Now, if you only look at the top half, cover that bottom one. Do you see a pyramid again? So there is a pyramid going from the base to the top. But there would also be a pyramid underneath it. Right? If we just rotated those around. We've got a pyramid on top and we have a pyramid on bottom. And so the name is trigonal bipyramidal. Wow, that was a lot, wasn't it? All right. Now, because it's 0, now that is, the angle is 120 degrees and 90 degrees. So now we're going to do the 5-1. I apologize, this is a long video. We're not through yet because we got to get through this couple of the 5s and 6s yet. If you need a break, just hit pause and walk away, come back. But the 5-1, the 5-1, take off one, put that in. All right, now it does matter which one you take off. You must, and make this a note in your side, you must take off an equatorial position. We replace an equatorial, or the lone pairs in an equatorial position, not an axial position. So this is what it would look like on the screen right now. Now, the name of this. The name of this one, I need to rearrange it. I need to tip this on its side. It's going to take me a second to try and get the right perspective for you guys. All right, I think that works. We're going to tip this on the side so that you see I've got my straight line, my axial positions, and they're kind of sloped down, like this one on the right's on the ground too. The other one's up in the air, and then it's sitting on a triangle base. Now, the name comes from the idea that this looks like a childhood playground toy. where maybe that end could go down and the other end could go up. And then you could go back again. And back again. Believe it or not. Well, believe it, because I'm telling you, the name of this shape, the 5-1, is the seesaw. Remember, electron geometry is always the same. We're just going to put a ditto mark there. It's trigonal bipyramidal. It's not a very good ditto mark. Let's try that again. Ditto. The molecular shape is called seesaw. They thought teeter-totter was, a little immature, so they went for the more sophisticated name, seesaw. That's the best they could come up with, so I guess it works. Now, what if we have two lone pairs? Again, let's put in ditto. The electron geometry is still going to be trigonal bipyramidal, but we are going to take off one of our bonds, and we're going to add in, I need to add in two regions, and again, they're both equatorial positions. So if I had this back in the original position, it'd be up there. But the name of the molecule, just look at the atoms, don't look at the electron clouds. What letter do you see on the screen? You see the T shape. That is the official name, T shape. All right, now we've got 5, 3. Ditto on the trigonal bipyramidal. What is the shape? If I have 3, well, we're going to remove pair. We're going to put in, whoops, I hit the wrong button. 3. All equatorial positions are now lone pairs. If I just look at the atoms, you've seen that before. That's linear, because there's more than one way to get linear. Okay, that wasn't nearly as funny. I try every year. All right. That is the end of the 5 geometries. Let's shoot for 6. Six regions, 0 lone pairs. Let's jump over to our model. I put 6. Whoops. All right. There is 6 regions. You got 4 around the center and 2 axial positions for equatorial. But let's take a look from the top. What's the angle between them? Between the equatorial positions. You see it's 90 degrees between all of them, right? What's the angle between the equatorial and the axial? Still 90. In fact, you can grab any atom and move it to I can try to the top position. They're all exactly the same. There is no difference. That wasn't true before. Trigonal bipyramidal, there were definite axial and definite equatorial positions. Here, they're all equivalent. Doesn't matter which one you put to the top, you always reproduce the same exact shape. All right, now, this would be a D8 for all you dungeon nerds. Wear it proud. It's but that's a D8 right there. But the proper name comes from the 8 sides. If you connected the outer atoms to the peak, you would get an 8-sided object, which is the octahedral shape. And since there's 0 lone pairs, octahedral. Alright, we're almost done. There's only 2 modifications on this one. There's a 6-1. So we go to a 6-1. Let's take off a lone pair. And let's put in, add a lone pair instead of a single bond. Now, for the name, it doesn't matter where you put it because they're all the same, but to create the name, we put it on bottom. So we see a pyramid hopefully again, but this time what kind of base is it? It's not a triangle base, it's a square base that forms a pyramid. So the 4-1, the electron geometry will still be octahedral, so we put a ditto there. On molecular geometry, we put a square pyramidal. Alright, now 6-2, ditto on the octahedral. What's it going to look like now? We're going to remove another one, and the lone pairs, whoops, always go in at the axial position. So you take off the bottom second time, or replace the bottom, now you'd replace the top. So now, what's the shape of the base? The base is still a square, and the base is completely flat. So you might remember that going back to the beginning. This would be square planar. Right, square planar. Alright. Now, had we done it the book way, I would have taught you all electron geometries. And then we would have went back through all electron geometries and done all molecular geometries. And I would have taught you this whole AB system that you would have tried to memorize that you really don't need. Now, what you do need, is to be able to draw a Lewis structure. From the Lewis structure, count how many total regions there are. From the total regions, and you look and say, of the total, how many are lone pairs? From that, you need to be able to give me the electron geometry and the molecular geometry of that compound. That's a lot, isn't it? And you're not going to have this chart. You got to memorize it. Well, there's actually 2 ways. I say memorize. That's what I did as a freshman. I know I copped out. I pretended it was a biology class and I just memorized the crap out of it. And I did okay. And you know what? If that's what works, great. What I'd suggest, though, is that you take the time, you build the molecules either physically or virtually. That you go back to that homework assignment on Lewis structures. And this is what I want you to do. That entire practice sheet of Lewis structures, I want you to take that list and I want you to not look at your answers. And what I want you to do is to make a table of Lewis structures. And then you're going to do total regions. And then you're going to do number of lone pairs. And then you're going to do electron geometry. And then you're going to do molecular geometry. And you're going to also leave me a column called hybrid orbital, which we teach later. I want you to take that entire practice list of Lewis structure compounds. Take the very first one, write its formula down. I don't know, let's say it was SO3. I'm not sure what the first one was. I want you to rework the Lewis structure. Don't use the one you've already done. I want you to practice this. And then once you're done writing your Lewis structure, then go look. Because on the test, 30 points of your next test is exactly what I've just drawn right here. I'm going to give you a compound. You will draw the Lewis structure. You will tell me the total electron regions. You will tell me the number of lone pairs. You'll tell me electron geometry, and you will tell me molecular geometry, and you will tell me the hybrid orbital. So if you can, this is the best way to get ready for that. All right. And then as you build these, either A, start memorizing this freaking table. Oh, it's a lot. But either A, start working on memorizing that, or B, start building them, start visualizing them, start seeing them. Start going, okay, I can see these sides. That's a trigonal pyramidal. But that comes from practice. That comes from doing this over and over. But I want you to practice your Lewis structures again, and then fill out this table. That's going to be 30 points right there on your next exam. All right. This was a big lecture. This is a big topic. I'm not going to put up a second video for you because this is what I want you working on. This table. Take the time, do it. It will pay off big time come exam time. If you're having any issues with these, again, we can talk on Discord. We can jump into Zoom. Trisha's there to help with tutoring. Whatever it takes, let me know. Let me know. Yeah, we'll end it with that. Thanks a lot. We'll see you guys next time.